Our last section in Chapter 7 is on Kruskal's algorithm. So this is our way of finding a minimum spanning tree. So it is still a spanning tree, but this one is a specific. Think about what we talked about at the beginning of the chapter, where we're trying to find optimal. That's exactly what a minimum spanning tree is. So your formal definition here is a spanning tree of a weighted network So we've assigned numbers now, like we did in Chapter 6. So we're back to weights along the edges. And we're looking for with the least total weight. So before we get into this, let's go ahead and review what we did yesterday. How many spanning trees exist in each of the given networks? Okay. Remember, in order to find that, we had to find the circuits within the networks. So if we look at this first one here, I've got a circuit of 3. And we have a circuit of 1, 2, 3, 4, 5. So we took 3 times 5, which gave us 15. Don't forget, because they share this line in common right here, we also have to subtract 1. So we have 14 possibilities here. Network 2, we've got a circuit of 3. We've got a circuit of 3. We've got a circuit of 4. These two circuits share a line in common, so 3 times 3 is 9, minus 1 is 8, and then multiply that by 4. That gives us 32 different options here. And finally, network 3, we've got 4, 3. This one is 3. And this one is 4. So 4 times 3, they share a line in common, so minus 1, that's 11. This is 4 times 3, they share 1 in common, so minus 1, that gives us 11. So 11 times 11 means I have 121 different options here. Holy cow. So this is why we come up with something called Kruskal's algorithm. How on earth can we find the minimum spanning tree without checking each and every one of these? I don't have time to do 121 options, and neither do you. So Kruskal's algorithm actually kind of reminds me of Chapter 6 when we did the cheapest link. I do believe it was section 6.8, the last section we did in Chapter 6. So we've got some steps here. Step number 1, first thing you want to do is pick the cheapest edge available. In case you have a tie, just randomly pick one edge. Mark it, highlight it, circle it. I don't care how you do it. Take a colored pen to it, a colored pencil. Somehow identify how you choose it. Repeat this step. Pick the next cheapest link or edge available and mark it. Okay, you've got 3 rules. Your rules change. Okay, rule number 1, you cannot make a circuit by choice. There are no circuits. Remember, spanning trees, no circuits. So if you want want to mark here. No circuits. Stop once you've chosen n-1 edges. Remember, edges are one less than vertices. So you can always count up how many vertices you have and then know how many edges you need. And vertices are allowed to have any degree that's greater than 0. So in other words, must be connected. Okay. We only have 2 examples, and then you're off to work on your homework. I will also open up the review. Okay, so you have that to work on. It'll be on Go Formative. And you'll have today and tomorrow to work on that. And then your test will be the next day. So, the following graph represents roads connecting 7 towns in a developing jungle region that's planning to lay fiber optic cable. The cost of laying the fiber optic cable is represented by the weights on the graph. So, the numbers you see represent the cost. It doesn't say dollars or anything like that, so let's just assume it's dollars. I don't know. Let's find the minimum spanning tree using Kruskal's algorithm. So, the easiest way to go about this is first off, identify how many vertices do I have? Okay, how many nodes or terminals do I have in this graph? So I've got 1, 2, 3, 4, 5, 6, 7 it looks like. So how many edges do I need? Well, I need 1 less. So I need 7 minus 1, which tells me I need 6. So, the way our method works, it says to identify the smallest first. So that's this one, 42. Keep identifying the smallest. So my next smallest connects B and D. That's 45. My next smallest connects A and D. That's 49. So I've got 3 edges now. If you want to keep a tally mark as you do it, that's fine. I need a total of 6. So after 49 is going to come 51. You cannot connect A and B here because that closes this off and creates a circuit, but I can use 51 here. Okay, so that's 4 now. My next smallest one is 53. That's 5. My next smallest would be 55, but that closes a circuit if I connect B to C. My next smallest is 56, but that also closes a circuit if I connect C and F. So then my final smallest is going to be 59, that connects out to E. That's a total of 6. Once you've reached the 6 edges, you are good to go. So your final step then is to add up all of these numbers. So we're going to add up 45, 49, 51, 42, 53, and 59. Grab your calculator. 49, 45, 53, 51, 42, 59. It's going to give us a total of 209. $199. Okay. Positives of Kruskal's algorithm. It's easy. Two, it's efficient. And it's optimal. Okay, so it doesn't require a lot of complex steps. It's easy. It doesn't take long. It's efficient. And it will always, always find an MST or a minimum spanning tree. Two more to look at. So, the one on the left has 5 vertices, which means we need 4 edges. So, smallest is 1.2, next smallest is 1.4, followed by 2.1, followed by 2.2. So we would add all these up. That's 2, 3, 4, 5, 6, 7, 8, 9. 6.9. And the one on the right has 1, 2, 3, 4, 5, 6 vertices, so we need 5 edges. My smallest is this 5 and this 5 here, so I'm going to use them both. They don't complete a circuit. Then I can use edge F to D, which is 10. My next smallest is 15, so that connects B and F. My next smallest is 20. I can't use edge E to D though, because that creates a circuit here, that little triangle down in the bottom. But I can use the 20 that represents A and E. So that's 1, 2, 3, 4, 5 edges. I'm good to go, so let's add these. 5, 20, 5, 10, and 15. So that's 10, 20, 40, 55. Okay, again, your homework for tonight is pages 267 and 268, numbers 19 through 23. Once you've completed that, you can go ahead and start working on your review, which will be on GoFormative. I will have it up on Canvas for you. And I will see you when we start chapter 8.